Thanks, Tina. So I'll talk about some probability elicitation that we did as part of the CReDo digital twin project. And this is joint work with a few people. So it was mainly me and Jim who did this work. So we led on the elicitation as part of CReDo. But we were also working with Chris Dent at Edinburgh, and Ben Maudsley essentially coded all the models for use in the final digital twin. So in case you weren't at Jim's talk or you've forgotten everything that he said, I'll introduce what CReDo was and then talk about the structural elicitation that very briefly that Jim talked about last time to set up the probability elicitation that we did. So CReDo stood for Climate Resilience Demonstrator, and the idea is that this was a digital twin as part of the National Digital Twin Programme in the UK. So what was the digital twin in this instance? Well, we were working with three different asset owners, UK Power Networks, Anglian Water and BT. And for a particular location in England, and the location chosen was King's Lynn, and I'll show you where that is on a future slide. What they did was they mapped out all of the infrastructure assets within that particular region of England, the particular place in England. And so this is part of the result of that, and the result was called a knowledge graph. I didn't come up with a name, but I think it's quite cool. But the knowledge graph looked a bit like this, and what you had nodes in the knowledge graph, and this represented physical assets that belonged to one of these three asset owners within King's Lynn. So this is a primary substation, this is a power asset, here's a secondary substation, here's a telephone exchange belonging to BT, here's a water subsite belonging to Anglian Water. And contained within the node was lots of information about what that asset was. So not only exactly where it is, sort of longitude and latitude, but also exactly what's there. So what the purpose of the thing is, what physical infrastructure there was at that location, but also for the purposes of a climate resilience demonstrator, any sort of defenses it had against sort of climate events. So things like barriers against flooding and those sorts of things. So within each of these nodes, there's lots of information about exactly what it is at this location, what this asset actually is. And then on top of that, we have the edges between the different nodes in this knowledge graph. And this was supposed to link sort of direct sort of dependencies within the network. So for example, the primary substation fed power to the secondary substation. So there was an arrow going from primary substation to secondary substation. And so all of these individual sort of nodes and links between them were provided by the individual asset owners. So the asset owner will tell us that the primary substation is physically linked to this secondary substation. But then what's sort of new in terms of the digital twin was then they also included the links to between different networks as well. So this is the first time they've thought about, well, this secondary substation, what does that link to? Well, this sends electricity to this exchange here. That's owned by BT. It also powers this water subsite here, and it also powers this sewage subsite here. So they also included all the links between the three different infrastructure networks. So we now know that if this thing failed, then it would take out this exchange and this water subsite in these different from these different asset owners as well. And so the result was the digital twin sort of had all of these different relationships between all of the assets within this particular region, between the asset owners as well as within them. And the point of this, the reason that they were interested in creating this digital twin was then to try and work out how resilient the network was to major climate events, and hopefully therefore put in plans to improve resilience across these infrastructure networks. And that could be as simple as sharing information in the event of sort of a big weather event. And so in order to use this knowledge graph to sort of think about resilience to climate change, there was then a set of technical work which was carried out by various people. And the idea behind the technical work was this. So we would start off with climate scenarios. So based on climate models, we would think about climate scenarios. What is the future climate going to look like in and around King's Lynn, the area that we were interested in? From these, we would then define extreme weather scenarios. So imagine that in a particular 24 hours, 40 years in the future, once climate change has had its effect, in King's Lynn, what would a big rain event look like, for example? What would a 1 in 10 year flash flood look like for example. And so these climate scenarios were then turned into these sorts of weather scenarios. And the weather scenarios that they were interested in were flooding scenarios. And so then some more modeling based on a model called HiPIMS, which is a model that turns essentially rain fields into which bits of a particular place are flooded or not over certain timescales. Then, so it's a big physics model essentially. So these weather scenarios, or rainfall over a 24-hour period, for example, were then turned into flood depths over that same period. So for those 24 hours, representing again an extreme flood, a 1 in 10 year, a 1 in 50 year, having observed climate change. So now these extreme events were more extreme than they would be right now. And then for a particular scenario where we've got these flood depths for the sort of from the start of the scenario to the end of it, or a 24-hour period, for example, they then wanted to say, well, what's going to be knocked out? Which of these assets are going to continue to function, and which of these individual assets within the knowledge graph would fail as a result of this flood? And so getting from these flood depths to which assets were working, that was what Jim and I were tasked with doing. And the information in the knowledge graph, well, it gave us a starting point for this, but in order to get an idea on the probability that any particular asset would be working or failed at any particular time in these scenarios, would require us then to talk to each of these asset owners, BT, Anglian Water and UK Power Networks, and work out exactly what they would do if their assets were getting flooded. So what action would they take? What typically would happen? What level of water would cause things to fail? So we needed to get that information from them. So we were going to do that via expert elicitation alongside the data that we had. And then what our stuff was going to be used for, there was then an operational research model, a sort of big optimization thing, which would then take these probabilities of failure of each of the individual assets and then simulate essentially cascading failure through the system. So if this power thing failed, what effect would that have on all the things that depend on it? And then of course the really big serious events would cause big cascades of failure and take out things across all three networks. And that's really what we're trying to get an idea of here. So the idea was to build this general structure and then apply it to a particular climate hazard, this flooding, in a particular location. So to show what these scenarios might look like and what that might tell us about how resilient this combined infrastructure network was to these future extreme climate events. And so, as I've said, the application that we looked at was in King's Lynn. And so if you don't know where King's Lynn is, and there's no particular reason why you would, here's sort of the bottom half of England. So this is the south of England, essentially. And here's Wales. And King's Lynn is here, it's in Norfolk. And Norfolk is a very dull place and nothing really happens in Norfolk. The only interesting thing to know about Norfolk is it's incredibly flat. So there's no hills or sort of mountains or anything like that. It's an incredibly flat place. And so here's King's Lynn zoomed in on Google Maps. And so you'll see that there's quite a big river that runs just down the side of King's Lynn here. So this is the Great Ouse, the river, which is a good name for a river. And so any flooding event really would have quite a strong effect on this river here. So this is the area. Well, this specifically isn't the area. This is just what Google Maps classifies as King's Lynn. But essentially, this sort of area is where we were thinking about in CReDo. So we're focused on possible future flooding scenarios. And we're thinking about a time period of sort of 40, 50 years in the future, 30, 40, 50 years in the future, when climate change has sort of had an effect and the climate is different than it is now. So they're the sort of weather events that we were simulating based on those assumptions. But we had to make the assumption that the infrastructure, so the power assets, the water assets, and BT's assets were as they are now. And of course, that won't strictly be true, but it'll give us an idea of the current resilience of the system to future climate scenarios. So what did we do in terms of getting at the asset failure probabilities? So if we're thinking about a particular scenario and we've got all this flood depth data, how then would we get to the probability that each of these different assets in the network would be working or not? Well, we conducted 2 rounds of structural elicitations, 1 meeting in each round with each of the 3 asset owners, so 6 elicitations in all. And Jim talked about these at length in his talk, so I'm not going to go through them in any detail, but I just want to show you essentially the output from this. So as a reminder, it was BT, Anglian Water and UK Power Networks who we were talking to in each of these meetings. And what we are trying to get at in these structural elicitations is all the relevant events which affect whether an asset is functioning in these flooding scenarios that we were thinking about. So in particular, what sort of failure modes might you envisage in an extreme flooding event? How might you go about trying to avert those failures? What action would you take? And what's the sort of unfolding set of events which would lead to failure or not failure of an asset? So that's what we were trying to get at here. And we built our general model structure. And so this is for a general asset, not thinking about a specific power asset or a specific water asset, but just for a general asset from any of these three asset owners. We built a very general model as a Bayesian network to encompass all the things that were important to decide whether or not these things would be failed or would be working. And so this is the final Bayesian network that we had, linking, well, the probability of failure at the end from this weather event, this extreme flooding scenario that we would be basing all of our conversations with the asset owners in, that we were essentially conditioning on in order to think about what things are going to fail. And I'm not going to go through this in detail. Jim talked about this a fair amount in his talk, but I just want to point out a few things. Critically, of course, asset wetness. Once things begin to get wet and get underwater, then they're more likely to fail. And so this was particularly critical. And so how assets could get wet essentially was at the crux of this model. And one thing which was really important and is relevant because all of this is very temporal, is remedies. So all of the asset owners have lots of actions that they can take if either they're worried that there's going to be a flood around one of their assets, or if there is already a flood sort of starting around one of their assets. Simple things like take things upstairs, wrap things in plastic, put up temporary flood defenses, bring in big lorries that can pump water out. So there's lots of things that they can do, but whether or not they can do them depends on two things. So it depends on surprise. So have they actually got any knowledge before the flood happens that a flood is going to happen? So can they put things in place in advance? But also access. So once the flood started, are the highways clear? So, or are they flooded, or are they full of people panicking and trying to get home from work because there's a flood happening? And are they allowed to go there? So the police will tell them whether they're allowed to use certain roads or not in the middle of a flood. So there was sort of this bottom part of this Bayesian network here was in general a really important part, because as the flooding event unfolds, whether or not they can fix things that are down or prevent them going down in the first place was a really important part of what the asset owners would do within a flood. So that was our general model. And then you might expect, and indeed you'd be right, that there are sort of hundreds rather than tens of different assets across the three different asset owners within the sort of King's Lynn and surrounding that we were thinking about. And so we need to be thinking about failure probabilities for all of those across each of the different scenarios. And so there's no way we were going to do that all via elicitation, sort of in a careful and sensible way. And so what was done in CReDo was initial ballpark estimates of failure probabilities were produced for each asset for each incident. And so these were based on, it might be the next bullet point, these were based primarily on simple rules. So if we know the flood depth at an asset location and we know a little bit more information about the asset and the location, then that spat out a probability at a particular time point that asset would be working or not. And so this allowed us then to run this climate change demonstrator and show what it might look like for a particular future flooding scenario. But of course, we had to have some trust in this simple rule that it was giving things that, okay, they're not going to be exactly what the experts would believe if we did this really carefully, but at least it's giving something which is vaguely plausible. It's not saying that the probability is 98% that it's going to fail when the experts actually would think it was unlikely to fail in this particular time in this particular scenario. So to help calibrate this rule, to make sure we were getting this rule sort of at least vaguely close to some sort of reality in terms of what the experts would believe for these failure probabilities, what we did was we ran some more focused elicitation sessions on a single particular asset for a particular flooding scenario. And the idea was to compare that to what the simple rule would say in this situation and see whether, at least for this place, for this particular scenario, are we somewhere near where we should be. And the proviso there is, were CReDo to continue and be footed in future years, then we could then extend this idea and essentially do a better job of this simple rule by picking a couple more assets, thinking about some more future scenarios, doing some careful elicitation, and then setting up a more complicated rule to give these failure probabilities that's consistent with all of the elicitations that we've done. So this is what we'd like to do were we to have more time and money. So the asset that we chose to do this more focused elicitation on was an Anglian water asset, and it was a particular pumping station. So it was a water pumping station. And so what we did was, first we needed to turn that really large Bayesian network, which contained anything that could happen at any particular asset, into a specific Bayesian network for the pumping station in question. So we then talked to Anglian water again, and again, Jim led this structural elicitation to refine the general Bayesian network to come up with a more specific Bayesian network for this pumping station. And we did it within a particular flowing scenario, and I'm not going to read this whole thing, but essentially the story we gave them, the flooding scenario that they got, alongside flood depths at this particular pumping station, was given by this story here. So it's a pretty extreme flooding event. We've got a river which is close to bursting its bank. We've got a sort of a full day of quite high rain, and we've got a quite unexpected event. So flood information is available only after the incident. So we've got quite an extreme event, also contained with a bit of surprise. So this feels like something where the asset would be under pressure, and there would be some chance that it might fail. And so, based on these structural elicitations, we came up with a much simpler Bayesian network specifically for this pumping station. And I guess the most important thing to note about this Bayesian network is that the main failure mode that the engineers at Anglian Water were worried about was that essentially some water would get to the main part of the pumping station and would cause essentially an electrical fire, which would then take out all of the electronics in the pumping station, and it would fail that way. And then if the backup power didn't work or was forced to run for longer than it could, then that would cause a failure. So that was the main failure mode that they were particularly worried about for this particular pumping station. And so then we needed to write down the model for the probability of the failure of this pumping station, so that we could think about all of the individual probabilities we would need to elicit in order to get a handle on that overall probability of failure. And so, in particular, the probability of failure was taken to be the sum of the probability of this main failure mode that they were worried about, and the asset has an electrical failure caused by water getting in, plus the probability that there's a power failure into the asset. So if there wasn't an electrical failure, then if there was no power coming into the asset, again, you would have backup power that might work. But if the backup power either failed or ran out of diesel or whatever, then you would have a failure of the asset like that. So it was an electrical failure really we were worried about here. And in general, for the elicitation, we give the opportunity for each of the failure probabilities I'll talk about on the next slide to depend on the height of the flood outside the asset, which we call D, so the depth of the water outside the asset, and also the height of the flood barriers at the asset. And for this particular pumping station, it has some permanent flood barriers that are 900 millimeters, so 90 centimeters tall. So that's a sort of critical height for the flood in terms of it overtopping the barriers and getting access to the pumping station. And so for each of these two different types of failure, an electric failure within the pumping station or a power failure coming to the pumping station, we then disaggregated them into some probabilities that we could elicit from the engineers at Anglian Water. And so in particular, for there to be an electric failure, the pumps would need to get overwhelmed. So the pumps in the pumping station would get overwhelmed. And then given that they got overwhelmed, water would then need to sort of essentially come up from the wet well into the building. So the probability that water gets into the building, given that the pumps are overwhelmed, and then there would be an electrical fire, given that water was in the building. So we then needed the probability that there would be an electrical fire, given that water had got into the building in this way. And for the probability that there's a power failure coming into the asset, well, there could be a power failure upstream of the asset. So the probability of U here is the probability of an upstream failure coming into the asset. So something upstream of this particular pumping station has failed, and therefore electricity isn't getting to us. Or there's a transformer just outside the pumping station. So, or the transformer could fail. So plus the probability that the transformer just outside the pumping station might fail. That would also cause a power failure coming in. But alongside that, the backup power would kick in if there was a failure of power coming into the station. So we'd also need the probability of the backup power failing to operate when called, which is the probability of the event C here. So it's combinations of different events which could cause each of these two failure modes. And so each of these different events here were the probabilities that we needed to elicit as part of the elicitation session with Anglian water. So how did we do this? Well, we elicited each of these probabilities from 4 different experts at Anglian Water, and it was a good set of experts because they span different expertise at Anglian Water. So we had the person who was the sort of engineer in charge of this particular pumping station, so knew exactly what was going on sort of on the ground at this pumping station. We had someone who's sort of responsible for sort of flood prevention, sort of preventing bad things happening in extreme weather at Anglian Water. So part of that team, we had someone a bit higher up who sort of overall had sort of a risk portfolio at Anglian Water, and then we had someone sort of a bit closer to the ground again, not responsible for the pumping station, but responsible for sort of for risk at a more technical level at Anglian Water. So we had sort of a range of experts in our 4 experts. And we had a single 2-hour workshop, so this wasn't very long. We had quite a lot of probabilities on that previous slide, and we didn't have very long with them in order to elicit them. So this was necessarily done relatively quickly. And so what we decided to do was we decided to use a reduced version of the Sheffield elicitation framework. And in particular, what we did for each of the probabilities that we elicited, well, okay, fine. Before we elicited each of the probabilities that we were going to elicit, we introduced the scenario, so that text that I didn't read through on a previous slide. We talked about which pumping station it was, so everyone was on the same page with that. And then we defined each of the probabilities of interest. So we did that at the start of the workshop. We did that quickly at the start of the workshop because we'd sent all of this information to the experts in advance as part of an evidence dossier. Similarly, we talked about what we meant by probability and what subjective probability is. And again, that was part of the evidence dossier that we'd sent to the experts in advance. And then we did a practice elicitation, and we talked about the probability that, in the views of the experts, the distance between Edinburgh and Glasgow was above a certain number of miles. I think it might have been 70 miles. And it turned out that if you work for Anglian Water, you have no idea where Glasgow and Edinburgh are. I have absolutely no idea at all about what the distance is between them. So that was illuminating in itself, but it gave them opportunity to see how the Sheffield elicitation framework worked, and also how hard it is to elicit, to think about your probabilities. So for each probability of interest, what we did was we first elicited the probabilities individually from each expert. So the experts thought themselves about what their probability was without discussion. They provided those, and then the group discussed the individual probabilities. So why individual experts gave what they did, what evidence they were basing it on, and why some experts were quite far from others in terms of the probabilities they gave. And then following that, we elicited a consensus probability for each of the quantities of interest. And the consensus probability wasn't something that the experts then suddenly thought it was their probability. So as usual, using the Sheffield elicitation framework, the consensus probability was the views of a rational, impartial observer who'd been sitting in the corner of the room, the team's room in this particular context, listening to the discussions, could feel sort of the relative weight of each of the points of view of the experts. What would they think? What would their opinion about this probability be? And so that was the interpretation of the consensus probability that we used. And so because this was done relatively quickly compared to a sort of full Sheffield elicitation, what I did was I just used a very simple tool using all of my Excel skills to manage to get a graph which changed when you entered things and changed them. I was quite happy when I managed to do that. And so this was the tool I used. So you had the quantity of interest. So in this case, it's the probability that the pumps were overwhelmed. Each of the 4 experts, so these aren't their real names. I was worried I'd be in breach of some law if I put their real names here. So these are some stand-in names. And then each of the experts, when they gave their probabilities, we entered them in the green boxes here. It created this part of the bar chart. And then we also worked out a mean, so the average of the 4 probabilities. And then when the experts gave their consensus, we added that as well. reflection on the way that I did this elicitation using this spreadsheet here. It's the first time I've done it on Teams, so as opposed to in person. It's the first time I've done sort of a Sheffield elicitation virtually rather than in person. And what I did was I asked the experts out loud for their individual probabilities. This was a really bad idea, and I shouldn't have done this, and we should have had some sort of online survey tool open at the same time, because essentially I think what happened was some of the experts were sort of moving their probabilities. Once Beth heard Aaron's probability, Beth thought, oh, mine was really far from there. And so I'm fairly confident that they sort of shifted that a little bit. And they were trying to justify their probabilities before experts had given other probabilities, which again isn't very good practice. So if I was to do this again in a virtual platform on something like Teams, I would have some sort of online survey tool open at the same time, so that the experts are giving their individual probabilities without hearing the probabilities of the other experts. But having said that, we did get some probabilities for all the different things we were interested in. So in the top table here, we've got all of the probabilities that were the ones that I talked about on the previous slide that we needed. Ones for each of the 4 experts, and then the consensus probabilities in the final column. You'll notice that for some of these probabilities, I don't have ones from each of the 4 experts. In particular, the probability that the pump will fail, given that the flood is high enough to top the barriers outside the pumping station, all of the experts agreed that that was inevitable at that stage. So it didn't seem like a good use of our limited time to elicit that in the 2 different stages. We just kept that to be approximately 1. There are a couple of particular points about this pumping station, which are slightly unique, and that's that often the diesel can get stolen from this particular pumping station, from the backup generator, and the batteries can get stolen from the backup generator. So this affects the probability that the backup generator will work when called. And we didn't elicit individual probabilities from the 4 experts for this, because essentially the only person who really knew about this was the engineer who's in charge of this particular pumping station. Because he's the one who sort of inspects the backup generator every now and again. So the other 3 experts deferred those probabilities to that single expert. So that's why there's no individual probabilities there. One which is of particular interest is the probability of an electrical fire. You'll notice that one expert gave a reasonably high probability for this, and the others gave quite low probabilities. But then the consensus probability is high. So what happened in the discussion there was this expert 1, give a lot of evidence and really strong rationale for why they'd given a high probability of this event, whereas experts 2 to 4 admitted that theirs was a little bit more sort of guesswork, and they were less sure about this. And essentially expert 1 convinced the other 3 experts of their point of view on that one. And so this is a potential advantage of using a discussion-based elicitation. Because if we just took some sort of average of these 4 views, then we probably wouldn't end up with a high probability there. The bottom table is some probabilities that essentially aggregate up from the probabilities in the top table. So the probability of the backup generator failing was relatively high here. It was about a quarter of the time. The probability of this electrical failure in the pumping station, that was about 2/3. And the probability of upstream power failure was felt to be relatively low. So the main failure mode here is an electrical failure. That's what we're really worried about. And so what did that do in terms of the probability that the pumping station would fail? Well, if the depth of the flood water was below the height of the barrier, it was about 70%. If it was above the height of the barrier, it was 74%. So really it wasn't water getting in and over the barrier from the outside that they were worried about here. It was water getting into the pumping station from the inside. So the depth of the water directly outside the pumping station didn't have a strong effect on the probability of failure. So the resulting probabilities of failure are high, even with lower levels of flood depth. This was a bit of a surprise to our rule of thumb, because the rule of thumb dealt very directly with the depth of water outside the particular location. And the fact that there was a 900 millimeter barrier at this pumping station meant that a depth below 900 millimeters using the rule of thumb would have given a low failure probability for this pumping station. So our rule of thumb didn't do amazingly well for flood depths of below 900 millimeters here. And the feeling was that this scenario, the feeling amongst the experts was that this scenario was so extreme and there was so much water around King's Lynn that inevitably it was going to get into the pumping station and cause an electrical failure. That seemed to be, you know, a very likely thing to happen, and that's why these probabilities were high, and indeed higher than you might expect. So just to summarize in 1 minute, so CReDo was pretty ambitious, trying to work out the resilience of UK infrastructure to future climate change, where there's lots of uncertainty and lots of different things there. And CReDo will continue, and so further funding has been secured for another year and potentially another 3 years. Although what they're going to do with that money and whether they'll pay me and Jim to do any more elicitation, nobody knows. Expert judgment is needed in these sorts of complicated modeling problems of large infrastructure systems, because you're just never going to have all of the sort of granular data that you'd need on its own to do the modeling. From the elicitations, the most important expert probably of the four, certainly they were all useful in their own way, but of the four, probably the most important expert was the one who specifically was responsible for this pumping station, and he was sort of the lowest in terms of his position in Anglian water of the four experts that we have. So we don't necessarily want the people who are at the top, we want the people who know what's going on the ground. And finally, elicitation is pretty resource intensive. So, you know, this was all for a single asset, for a single scenario within the CReDo project. So how do you scale these things up? Well, that's a good question, and that's a question that we're being asked by CReDo at the moment. So that's everything, and so I'll stop there